In this video, I'd like to go over an example of a binomial distribution problem. We see here a recent study has determined that the smoking behavior of parents does influence their children's chances of smoking during their lifetime. So we find that 8% is the rate that we see for kids ages 11 or older whose parents were never smokers. So if a child is raised by parents both of whom do not smoke, we would see an 8% chance that that child eventually smokes. So we're going to see and investigate this using a particular family that contains 4 kids and both parents who are non-smokers. So we're going to have a random variable here. The variable is K, and this represents the number of Smith children who become smokers sometime during their lifetime. And the first thing we want to do is to create a probability distribution, and then eventually we're going to answer some questions about it. So again, we know that this is the binomial distribution because if we consider the variable, the number of children who smoke, consider each individual child. There are 2 choices here. They either become smokers or they don't. And we're not considering maybe they smoke for 2 weeks and then stop. We're just considering they either become a smoker or they don't. So we have 2 options, a success in this case. The success is, even though it's very subjective, the word success is just saying we have a positive outcome, that they do become a smoker, and the failure is that they don't become a smoker. So I'm going to type these in here. The probability of success, meaning the outcome is positive with regards to the rate here, is going to be 0.08. There's an 8% chance that a child becomes a smoker, so we're going to associate that with a probability of 0.08. With that, we know that Q is going to be the probability, it's going to be 1 minus P, which is 1 minus 0.08. This is the complement, this is the probability that they do not become a smoker. This is going to be 0.92. So we are looking at this family here, 4 kids, both of whom their parents are non-smokers. We have a few options here. We're going to look at those 4 kids. How many of those 4 kids could become smokers? Well, 0 of them could become smokers. 1 of them, 2, 3, 4. These are the outcomes. We either have 0 children, 1, 2, 3, or 4. All of them become smokers. So what we're going to do is use this idea of the probability distribution, fill this out using the Binomial Calculator. If you had class with me, I showed you how to do that within Minitab. If you are not going to use Minitab, there are lots of ways that you could calculate the different probabilities for 0, 1, 2, 3, and 4. One thing that I decided to do was to go onto Google. I Googled Binomial Calculator, and I'm just going to click on the very top link here, Binomial Calculator. And I'm going to use this to help me calculate each individual probability, the probability of having 0 children out of the 4, 1 child out of the 4, 2, and so forth. So these are the pieces of information that we need. The probability of success on a single child, or a single trial, which in this case it's going to be the rate that the child will begin smoking. So the probability of quote-unquote success, the rate of them becoming smokers, is going to be 0.08. We need to make sure, since they're asking for probability, we're not going to put in 8, because if you put in 8 as an 8%, they're looking for probability. Probability needs to be between 0 and 1. The number of trials. This is telling us n, right? And we know in this particular problem here, n is equal to 4, and this represents there are 4 children. 4 children, which represents 4 possibilities. Okay. So there are 4 trials out of a sample of 4 kids is what we're looking for. We want to know, first let's calculate the probability that 0 of those children smoke. So I'm going to type in 0. Again, just looking back here, there's a probability of 0.08 for each child. There's 4 trials, 4 children. We want to know what's the probability that none of them, 0, smoke. So when I hit calculate, notice it's giving me the probability. This first one is the probability that we have exactly 0 children. That's 0.716. So I'm actually just going to round this to the thousandths place, 3 decimal points, 0.716. That's telling us the probability of getting exactly 0 children who smoke out of the 4 is about 0.716. This next one down here says the probability of having less than 0 children smoke. Well, that doesn't make sense, right? This is less than 0. You can't have less than 0 children smoking. This is less than or equal to. This is the probability that we have, this is the probability that there are more than 0 children smoking. In other words, we would phrase this as at least 1. That's 0.28. And this is the cumulative property 0 or more. And obviously that's going to be certain. Either 0 or more are going to become smokers. You can use these to help you for sure, but I'm just going to go in and find the probability for each one. In other words, let's now plug in 1. What's the probability out of 4 children? The number of successes, the number of children who smoke. What's for 1 child? We'll plug in 1, hit calculate. The binomial probability for exactly 1 child is 0.249. So I'm going to put that in here. 0.249. And I'm just going to repeat this. If you have Minitab, we know, as we saw in class, that you can make a column of these values. So and then ask Minitab to look for that column to calculate the different values. So now I plugged in 2 for exactly 2 children, 0.033. 0.033. Now I'm going to do 3. This isn't too bad. I don't mind putting all these in because we only have 5, 0, 1, 2, 3, 4 that we're doing. The probability that exactly 3 is 0.00. We're going to round that up to 2. And then finally, what's the probability that all 4 are smokers? It's going to be a very small number here. So there's going to be essentially it's going to be 0. But it looks like it's going to be 0.00001. Or excuse me, 0.0005. So let's put that in. 0.12345. Again, that's a very small number. I know I said to round to the third decimal point. It's okay that we can leave it like this. So this is just this is creating the probability distribution. It's a probability distribution because we're describing a numerical random variable. All of the probabilities here, if you were to add these up, they're going to add up to very close to being 1. They're going to add up to essentially 1. And what this is saying, again, is every single outcome is included in this within this probability distribution. This chart here accounts for all outcomes and the likelihood of each one of those outcomes. So this is what I would be expecting for if I asked you to create a probability distribution for K. Now let's go down here. Next, what is the probability that none of the children, the Smith children, turn out to be smokers? Well, we can look up top here and we see the probability that exactly 0, right? That's the same thing as none. So the probability of exactly 0 children is going to be equal to, well, looks like 0.716. That's pretty simple. What is the probability that at least 2 of the children become smokers? So the probability of at least 2. We could plug back 2 back into our calculator and look at the cumulative probabilities. Or you can think to yourself, if it's at least 2, this is the probability that there's 2 children, or there could be 3, or there could be 4. Oops. So we're going to add all these probabilities up. If there's at least 2 children who become smokers, we can add these 3 columns up. So that's what I'm going to do. 0.033 plus 0.002 plus 0.1234. We get, when you add all those up, again, we're adding these columns, we're going to get 0.007 0.03505. Okay? So we could do that again by plugging in and just adding, using our probability distribution, we can just add 2 and 3 and 4. Or if you want to, we could go over here, plug 2 back in, right? 2 for the number of successes, 2 children out of 4. We see, it says right here, the cumulative probability, the probability that we get 2 or more. We're using this one down here because it's greater than or equal to. We're including 2, right? We're including 2 or more. This one is just saying strictly greater than 2. This is saying exactly 2 or more. And notice we get 0.0344. We're going to have a little bit of a rounding issue, but it's very close. 0.035, 0.034. Very close. You can do that again using this calculator if you have this calculator, or using Minitab you can change it to cumulative. Or you could just use the probability distribution, add 2, 3, and 4. Okay, and then finally, calculate the mean and standard deviation. Remember, the mean of a binomial distribution can be found by taking n times p. In other words, the number of trials, which in this case the trials is the number of children, 4, and times the probability of success, quote-unquote success, which we know to be 0.08. So the mean, which is 4 times 0.08, is going to be 0.32. We want to associate this, even though that looks like 0.32, that's a very small number. Don't lose track of what the mean is. The mean represents the expected value, or the expected outcome. That's the same thing as the mean in terms of a probability distribution. It's not to say we're always going to get 0.32, but this is suggesting that the expected value or the expected outcome of this, we would expect 0.32 children. That's not even one child, right? It's less than one child to become smokers in their lifetimes. That's what they're doing here. The standard deviation can be found by taking the square root, so I'm just going to write in square root, of n times p times q. The square root of n times p times q. So that's going to be the square root of, well, n is 4, number of trials, p is the probability of success, which is 0.08, and q is the probability of failure, which is 0.92. Remember to take the square root of that whole thing. So the square root of 4 times 0.08 times 0.92, we get 0.543. I'm going to round that to the thousandths place there. Remember, why would we even want to find the mean and the standard deviation? The reason why is because we can find an acceptable range, or the quote-unquote usual range. And this can be found by taking the mean plus 2 standard deviations and then taking the mean minus 2 standard deviations. All right, so the point of this is to find a usual range. What would we expect given the probability of quote-unquote success? What would we expect? So if we take the mean of this probability distribution, which is, where was that? 0.32. Okay, so 0.32 plus 2 times the standard deviation, we're going to get an upper bound. So 0.32 plus 2 times the standard deviation. Whoops. We get 1.406. And what does this represent? This represents the upper bound of the quote-unquote usual range, the rule of thumb that we saw. If we do the same thing but we take 0.32 and subtract 2 standard deviations, we would get negative 0.766. And this represents the lower bound of the usual range, of the usual range. Okay. What is this saying again? Using the mean and standard deviation, we could say we're approximately 95% confident. In other words, we would expect values to fall between negative 7.66 and 1.406. In other words, if we saw that one child, let's say you were asked, is it unusual, would it be unusual if one of the children of the Smith family, would it be unusual if one child ended up becoming a smoker? Well, we can look at this usual range using the mean and standard deviation. One child is contained within this interval. So we would say that it would not be an unusual occurrence. That would not be an unusual event. If I said, what about 2? Would it be unusual or unlikely if 2 children out of the 4 became smokers, knowing what we know about the rate? Well, we can look up here and see, well, it is a very small probability. Or we can look down here at the usual range. We see 2 falls outside of this range. So you could say, since 2 is outside or further away than 2 standard deviations, we would take that as an unusual outcome. This, again, is an example of a binomial distribution. We know the probability or the rate, in this particular case, to give you a percent, we know the probability of one success or one failure. And what we want to know is, out of an entire sample, out of, let's say, 50 people, 100 people, is it unusual if we saw 3 people? Or what's the probability that we found that for the Smith family with 4 kids, what's the probability that exactly one of their children does become a smoker? Well, we found that with our probability distribution using a binomial calculator.